So welcome everybody to this special seminar just before Christmas. It's my pleasure to introduce you to Thong Nguyen. Nguyen.
Nguyen, as Vietnamese name.
But you can call him Tom, right?
Yeah, Tom and Jerry. Yeah.
And he's been visiting us for a few weeks. He's been here since last week. And he's coming from Oskar Klein Center. He's a second-year PhD student, but he has already quite some experience. He's done his undergrad in Vietnam, in Saigon. Then he moved to Paris to do his master's. And now, as I said, he is in the Oskar Klein Center doing his PhD under the supervision of Tim Linden. Just to say that he's a very advanced student. He already has how many papers? 7 papers, where you are the leading author. So very strong record for a second-year PhD student. And he's basically working mostly on dark matter detection, and he will be here to collaborate with us and with a group of astroparticle theory or anybody who is interested in his science. So thank you, Tom.
Thank you, Jorge, for a very nice introduction, and also thank you everyone for having me, especially Christmas is coming close. So, so today I'm going to talk about my previous work and also like ongoing work with the people at Stockholm and also like outside collaborator, mainly about the dark matter, like how to detect dark matter like from outer space and also like from extreme environment. And the outline of this talk is I expect that like I'm talking with a general audience, so I will give a brief review about dark matter, like the motivation, the models, and all the conventional detection methods right now. And then I will more focus on the thing that I was thinking about recently, like indirect detection of dark matter, and more focus on the dark photon dark matter candidate. And then I will go completely a different direction to talk about how to detect dark matter using celestial object. And by the end of this talk, I will have an advertisement for if you want to come to Sweden to meet us to give a talk, etc. Okay. So this talk is actually based on my 4 previous paper with my collaborator, and also 3 incoming, with 2 of them will going to be submitted to PIL. And yeah, so first of all, I will start with the question: why dark matter? Why do we physicists care about the dark matter? So if you a physicist but really bad at chemistry, like I am, who like cannot remember the periodic table, this is what particle physics offer to you. So here is standard model, is describe all of the matter in the universe. Like we have the quark sector, and we have like the lepton sector over here, with all of them fermionic particle that make all of the matter in the universe. And then you can also have all of the interaction all the particles that carry out all the interaction. Beside gravity, we have gluon for strong interaction, photon for QED interaction, and Z and W boson for the weak interaction. And then we have the Higgs particle to basically give you the mass. But then astronomers actually they disagree with the particle physics, because like they found, for example, like in here, something that particle physics, the standard model cannot explain very well. So in here, I show you one of the an example, the rotation curve of a spiral galaxy, Messiah 33. So particle physics, they use like Newtonian dynamics, and they calculate the theory line on the dashed line over here for all of the visible matter. But they disagree with the observation for the rotation curve that actually go pretty flat if you go into very far distance. Then this can be a hint of a missing mass that we didn't take into account some mass in here, beside all of the particle we know already, and also maybe it's a hint that we don't know gravity very well. So I'm a particle physicist, so I kind of biased in about the idea that we are missing something. So the way particle physicists do is they just add in another particle candidate that we cannot detect right now, and we call it the dark matter. And by doing that, we actually answer a lot of problems right now, but also we create a bunch another kind of problem. So we don't know what exactly dark matter, and we just only know that they interact poorly to gravity right now, and they have like 5 times much dark matter compared to the normal matter, and the rest is dark energy, which I'm not going to cover in this talk. Right? So to answer what is the nature of dark matter, particle physicists are actually really creative. They think of other kind of model to explain them. So in here, I show you a Venn diagram made by my master advisor, Tim Tay, and also with Tracy Slasher from MIT. It's also a very nice review particle. You can look at them. So you can see that they list all of the conventional dark matter model in here. So I want to point out in the yellow area is the axion dark matter, which kind of a trending right now. The other dark matter candidate is actually in the green, cyan, and orange. Stand for wind particle. Usually a very hot topic, but right now axion will kind of dominate right now. And in this talk, I will concentrate on the less famous candidate. First, I will concentrate on dark photon. It's like Luigi to Mario here, and also for the wind dark matter. So how to find dark matter? So assuming that dark matter also interact with normal matter with an extra interaction beside gravity. So we can just plot one diagram in here that essentially show all of the way to do the detection for dark matter. So I will go into the counterclockwise here. So from right to left. So you can produce dark matter by smashing 2 particle standard model particle together to reducing dark matter, and you're looking for like some mixing energy, some radiation. That's what CERN actually doing right now. And if you go from bottom to top, you can see that we can looking for more elegant way. We wait for dark matter to come into scattering with the standard model, and then we measure the recoil energy. So one of the famous experiment doing that is actually Xenon in Ransazzo, Italy right now, where they measure the recoil energy of nucleon and electron of dark matter scattering. And the other way is actually kind of very cheating, because like in astronomy, we have a lot of data from gamma ray, also, like from neutrino, X-ray, etc. And particle physics, we want to exploit those data. So we want to searching for the signal of dark matter annihilation to produce standard model like gamma ray neutrino. So then I will focus on the thing that I was thinking about recently is the indirect detection of a dark photon. So like I said before, dark photon is a less famous candidate compared to axion right now. But I hope by the first part of the talk, I will convince you that dark photon also interesting too. So the dark photon is, and also this is the only equation I will show in my slide. The dark photon is just a simple extension of the standard model. So you write out the Lagrangian, and you just basically you copy the QED Lagrangian, and then you add a dark photon term here with a mass here. So you have a massive dark photon, and then you add a third term that describe the mixing between the dark photon and the normal photon in here. And the mixing have the coupling. The coupling basically describe the interaction strength is epsilon over here. So if you want to know about the dark photon, there's a very nice review article written by 3 Italian physicists in here. So that's how I learned about dark photon before. And the two parameters, the kinetic mixing epsilon and the dark photon mass, are the targets for a lot of experiment and phenomenology study. So in here, I show you a result put by Kieran O'Hare and his collaborator. They wrote a very nice review article in 2021. Describe all the constraint, all the study before for the kinetic mixing and to the dark photon mass. And up to today, after 3 years, they have quite a lot of update for the result in here. And Kieran also like keeping all the update on his website, so you can check it out. In here, I want to spoiler alert. I want to show you our contribution to the hunting of dark photon. Is here. It's a very small here, but later on I will zoom in and I will show you how big it is. Right. So if you have a dark photon, dark matter, a massive dark photon with non-zero kinetic mixing coupling, you have to expect the dark photon have to be decayed, right? So, for example, consider like the light is standard model particle. The dark photon have to be bigger than 2 times twice the mass of the standard model. So in here you can see that I show the diagram where dark photon mixing with the photon and the Z boson, because if you have a very heavy dark photon, you can also mix with the Z boson, the weak interaction, and then you decay to either like as fermion particles or W boson pair particle in here. But if you have a dark photon mass below the 2 times electron mass in here, you can actually decay to a very interesting channel that go to the 3 photon channel to interaction to a loop diagram in here. And if your dark photon mass is way below the electron mass in the loop, you can just integrate out to all the loops, and then you can use some kind of Euler-Heisenberg effective field theory to calculate the decay in here. So because of this shape, that's we call it the dark photon trident in our paper. They look like a shape. Someone also like argument they look like a fork. I don't know. Yeah. So first, so basically we investigate this dark photon trident signal in our research paper with my PhD advisor Tim Linden and Tim Tay. So we have an below MeV dark photon dark matter decay. So we expect the photon coming out will be around keV energy. So it will fall into the X-ray observation. So that's why we use the International Gamma Ray Astrophysics Laboratory Telescope, or short for Integral. And this telescope can observe the photon energy from 30 keV to 8 MeV. This is what they observe the data from Integral in here. So they measure the flux, photon flux over the photon energy here inside the galactic center. So we put that and we calculate the decay of a dark photon dark matter inside the near the galactic center. And here we sketch, for example, the flux in here for this decay. Well, as you can see, it's not a line. It's not like a one particle decay to 2 particles. It's not a line. It's actually a continuous distribution. But this in this telescope also observe some of the photon coming from other sources, from astrophysical sources that we treat them at background. So first we add in all the component or the background in here to improve our result. So first we add like some kind of spectrum coming from unresolved sources. The spectrum coming from inverse quantum scattering of cosmic ray scattering with the medium radiation field. And then we have the positronium decay of cool cosmic ray with the electron density. And also because like there's a 511 keV line, we add another barium nuclear line coming from massive star to fit the result much more precise. And our result and our figure actually chosen by the European Space Astronomy Center to be the September picture of the month. All of the result in here produced using the template by a beautiful template by Francesca Calore, Thomas Seeger, and collaborator that you also can download it and try to fit to find your dark matter by yourself. So after we do the fitting with the X-ray data, we will do the constraint on the lifetime of the dark matter, dark photon, dark matter. So in here, I show you our result is 1 or 2 order of magnitude stronger than previous result, and from the constraint on lifetime, we calculate back to the constraint on the kinetic mixing and the dark photon mass in here. So I want to notify you something. In here, our constraint are very strong, especially at 1 MeV, and it's going like the slope is going down really much. That's because we take into account the loop calculation in particle physics. Previous result they didn't use they didn't take into account the quantum correction in the loop diagram, and they just use the effective field theory approximation. So our result also demonstrate the importance of particle physics in terms of study astroparticle. Moving on, like we ask the question, okay, what if the dark photon is heavier? How can you detect them? So for heavier dark photon, they will dominate the decay. The dominant decay channel will be all the fermion and maybe the W boson, and all of them maybe like you decay to some fermion and they will radiate to photon, or they can decay back to photon, and then we can also using integral to observe the signal. And for the dark photon, it's not only decay to electron, positron, they can decay to all of the other particles. So in here, we actually take into account the full branching ratio for the dark photon to in our calculation. We put the dark photon model in our analysis, and also we extend the analysis result up to AMEV X-ray signal, and we also include several nuclear lines to fit the spectrum better for the heavier dark matter. So in here, and okay, and another way to detect this decay signal is because like they can decay to electron, right? There are also another instrumentation that's very sensitive to cosmic ray positron. That's the alpha magnetic spectroscopy, or AMS 02 in here. So Isabel John is one of the member in our group who do the fitting with the cosmic ray spectrum. So as you can see in here, she have a model of all of the background, astrophysical background, and then the spectrum coming from dark photon decay. So even with a very small branching ratio for electron positron, they can also produce a very sharp spectrum in here, hinting that the experiment are very sensitive to like model that can produce electron and positron. So we do the same. We constrain the lifetime of the dark photon, and using integral and AMS, and then we provide the constraint on the kinetic mixing with the dark photon mass, and that's the result on my previous paper. But that's not enough. We actually want to build a template to study all kind of dark matter model, not just the dark photon. And we're also like thinking about using different X-ray observation or any kind of observation. So we're building a team right here with Pedro de la Torre Luque, which is the name very long, from Madrid, also Sam Balaji in King College London, and Isabel. To we will put up another paper this January soon to consider multiple dark matter candidates. So okay, so let's do something more fun, which actually the thing that I'm also concentrating doing right now is using compact object or celestial object to detect dark matter. So in here, I show you, for example, 4 of the celestial objects. I have considered, for example, like Jupiter, neutron star, round dwarf, and also like the most peculiar object, is, at least for Stockholm people right now, the sun here. And so the way we use the celestial object, for example, like Jupiter in here to study dark matter, it actually, the object can capture the dark matter. So if you consider a dark matter going to the object and then scattering with the nucleon or electron inside the star, right? Then they can lose kinetic energy, so they can scatter one time or many times. And after their kinetic energy reduced to below the escape velocity of the star, they will be captured. So the idea is very simple. And then after they are captured, 2 dark matter captured inside the star can annihilate to each other to produce some signal. So for example, in here, I show you one of the cartoon where they annihilate to some dark photon dark matter, some dark photon particle. And though dark photon, because it's very weakly interact, they will escape the star, decay to photon, and then can be picked up by the observation. For example, like Fermi telescope in here, or also like CTA has multiple gamma ray observation. So first, let me go to some of the signal and observed by gamma ray in gamma ray observation. So first, here is the signal coming from Jupiter, dark matter capture and annihilate inside Jupiter, and this is the data from Fermi. So we actually calculate the gamma ray flux coming from dark matter annihilation inside Jupiter, and then we fit with the Fermi data. We also do the same for the sun, using the Hawk data with very high energy. This is actually a very interesting article that I can discuss with you after this talk. It's called The Sun Anomaly. It's a very interesting article. But so far, we're just using the upper limit from Hawk to constrain on this detection signal, this annihilation signal from inside the sun. And we can go further. We can go to further inside near the galactic center and doing the same for all of the round dwarf in galactic center. So we calculate the signal of all of the round dwarf. We integrate the number density of all of them inside the galactic center, and we use Fermi to constrain on the annihilation signal. We also do the same for neutron star, but for this kind of energy, we need to require heads, and later on maybe CTA and lasso. Yeah. So after that, by measuring the detection signal coming from the object, we can actually put the constraint on the cross section of dark matter interacting with the nucleon inside the star. So we measure some annihilation signal, but we put the constraint on the dark matter with nucleon signal. It's kind of cool. So in here, I show you the new result from Jupiter, which can go down to 10 MeV and push down the limit like 2 or 3 order of magnitude. And also the result coming from galactic center round dwarf, but we vary the dark matter density profile because there's a different way to fitting the signal with whether or not you use NFW or generalized NFW profile. And we do the same for the sun and a neutron star. So for the sun, actually, our result already covered by direct detection from xenon, so it's nothing new. But for all the galactic center neutron star, we with the kind of appropriate profile, you can actually push down to the xenon neutrino force. This is the right area over here. So it's kind of promising because like xenon neutrino force is where you cannot distinguish between the dark matter coming in scattering with the detector or the neutrino scattering with the detector. So by doing this way, you also provide another way to probe this parameter region. So so that's for the gamma ray signal, right? But what happens if you consider neutrino? So neutrino is also a very weakly interacting particle. So if you annihilate, dark matter annihilate inside the star and produce neutrino, those can also escape the star without requiring some condition like long-lived mediator or something. So together with team Pierluca Carenza and Axel Wismar, we also will put in another paper this January where we consider neutrino signal coming from the annihilation inside the sun. So this is some kind of a preliminary result that I'm gonna show you. So in here I show you the, for example, like we're using a detector called neutrino detector called it Super Kamiokande in Gifu prefecture in Japan, and this is the atmospheric. This is the atmospheric muon neutrino background. With the super Kamiokande and the angular resolution, we can actually redo the background here. So our job is we calculate the flux coming, for example, like some annihilation signal directly to neutrino, to a long-lived mediator, and then mediator decay to neutrino, or even like go to a tau particle, and then the tau can decay to neutrino. So as you can see, they're very promising to super K is very promising to detect this signal. And then we calculate the constraint, and actually this is our strongest constraint on the leptophilic dark matter. So in here I show you the constraint using the super K with 10 years of exposure of the detector, and then we can push down the limits from 1 to 2 order of magnitude compared to the xenon 1T. So super K is a detector of 22.5 kiloton water, purely water. So with 10 years of exposure, we can push down this limit. And then we can actually do much better. We calculate the projection for hyper Kamiokande, which is a bigger detector, which actually have the exposure up to 187 kiloton water. So the constraint will much around like 10 times stronger compared to a super K. Yeah. So the next step in our group, we actually try to think of any other way, maybe using different celestial object, maybe using different phenomenology, you know, like neutrino, gamma ray, cosmic ray, and also you consider star formation from these the dark matter annihilation and capture processes. So together with Carlos Blanco, who right now is a junior faculty in Penn State, and with Tim, we are going to release another paper this January. I hope so. So the take-home message that I want to deliver to you guys is the celestial object actually can be act at the dark matter collider. They harvesting dark matter and then they collide them, and they can produce some multiple indirect detection signal. So they also have like huge potential to study new physics. And it's kind of free because like it's already there, right? You just need to build a detector to detect the signal from them. So I think this is a very big motivation. And finally, I want to advertise something we call the BSM seminar at the OKC. So I'm one of the organizers at the BSM seminar in there. So if you are a PhD student or young postdoc or junior faculty, if you getting sick of Spanish food and want to go to our wonderful cuisine in Sweden, please contact us. Me and Milena Chukonocevic, she is a postdoc in our group, and she also very fun to interact with. So we are the co-organizer and team and Christian arm in KTH, the one who actually funding this kind of meeting. So we can like invite you to Stockholm to give a seminar. We cover your flight and also 2 days at the hotel. Also unlimited IKEA meatball. So yeah, come give a talk at our OKCBN seminar. And one final thing, I will leave you with my favorite dark matter candidate, the dark matter. So thank you so much.
For the very nice and comprehensive seminar. Do we have questions? Indeed.
Maybe it's not directly related to what you talked about, more to your introduction. So you mentioned at the very beginning dark matter being a particle versus dark matter being effectively an effect of modified gravity. Now, I'm not an expert on dark matter, but there was this article which got quite some attention, something like a few weeks ago, where they claim that particle dark matter is dead. What's your opinion? What's your opinion on this?
Yeah, so actually I have to ask a question. Is that article coming from Sabine Hobsonfelder? Is that article coming from Sabine Hobsonfelder?
So what is the punchline, or why is what is that? It seems to be very difficult to kill. Yeah, I see.
Yes, so actually, if there's a lot of simulation that I won't say they are dead, but they actually rule out a lot of parameter phase space for particle dark matter. The simulation right now is also more favor on some kind of like fuzzy dark matter and wave dark matter. That's more on the wave property of the dark matter. Yeah.
I didn't notice it on the archive. It made it to the popular news.
Yeah.
That's dangerous. Yes. Yeah. Yeah. So yeah, I was gonna ask you. I mean, I see many students. If you have any questions, provocative questions, even you can ask Tom. If not, in the meantime, you mentioned in the very beginning. But I have two questions. One is related to Andy's, but less provocative. You mentioned the action. No, the action. So dark matter candidate is justified also by other reasons. No, I mean it gives a solution to salient problem of particle physics and the standard model, strong CP problem. And therefore, the action comes from free. That justifies, or that has justified historically the focus on action searches. While for the dark photon, I mean, you mentioned that you put the Lagrangian, but in principle is a bit ad hoc. No, I mean we can add it, but there is no a priori any justification to add it in the. For another justification that just explained dark matter, for instance, right?
Yes. So actually, axion is more favor in terms of theoretical motivation, where you have a generate mechanism. So for axion, you can have like misalignment mechanism, and then you generate even very light axion dark matter. For dark photon, you need to require the tuning for the misalignment mechanism. Also, maybe you have to come in from some explanation coming from inflation.
But even beyond that, I mean, the action solves the strong CP problem.
Yeah, axion can solve the strong CP problem. I mean, like QCD axion, right? So a lot of study right now focusing on axion-like particle that cannot solve the strong CP problem, but they just study it because like it can. So our motivation for the dark photon is also not really strong. We just say, okay, it still can be a dark matter candidate. So we just study them. Yeah. But about the strong CP problem, recently, and maybe we can discuss later, there's a article they debate about like,
I know.
The strong CP problem is
if it's a problem or not.
Yeah.
And I have more practical question in your model for the dark photon where you have the trident. If you go above the two electron mass threshold, I guess the problem is that the lifetime is smaller than the lifetime of the universe. Is that right?
The what? Sorry.
If you go above the 2 electron
Yeah.
threshold, mass threshold. Then this guy can decay at 3 level to 2 electron positron. And then I guess that the problem is that the lifetime, the parameter space, the lifetime of the particle is shorter, quite shorter than the age of the universe, right?
Yeah, so in here, I actually will do the constraint for both for the heavy dark photon. So we actually calculate the constraint for the kinetic mixing. If you have a dark matter that's the lifetime is smaller than the time of the universe. So if you can see, that's why people kind of refers light dark photon because the constraint is very strong over here. But and we can show that based on integral and AMS 02, they even provide stronger constraint. Actually, recently we kind of interesting about heavy dark photon because like there's an article say that inflation can only produce dark photon, dark matter, heavy mass, like heavy mass. For the light mass, a lot of parameters will be ruled out. So yes.
Okay, thank you, Tom. 2 questions, Fernando.
Thanks, first of all. And about the research you talk about with integral and the X-rays, no? The first, that flux data comes from a specific source or where does it come from, all the data you talk about in that one? Yeah.
This one, right? So okay, the data is the dot, the black dot over here. That's the data.
Yeah.
We just try to think of modeling a background model. So if, for example, like the background coming from the unresolved sources in here, we know that they have to have a generate feature, like they have a cut-off power law compared to the dark matter spectrum, which have a peak at some point and then drop down, right? So we just put all of them and we do some kind of macro chain Monte Carlo fitting. So for each dark matter mass, they will tune up the component of the background model. So there are some components where the background model coming from unresolved sources is very worse compared to the other. But basically, we just do the fitting and we find a 95% confidence level. I can discuss with you more later in the technical detail, but it's a boring slide. I don't want to put it.
The green region comes from the expected flux from the dark photons, no?
Yes. Some of them will come from the dark photon. Some of them will mainly coming from the inverse quantum scattering and the positronium spectrum to explain the 511
so
keV.
that green region is expected to be a background radiation from this dark photon. Okay. Vale.
Yeah.
Nice talk, Tom. Yeah, so I had a question as to whether you expect any of these models to have strong enough couplings to the standard model that you could create some heating. For example, if you had supernovae in galaxies, do you think this could have enough strong couplings to heat dark matter, at least locally? Is this possible? Or?
If you're interested in that question, I will send you a very, very nice article, also by my collaborator, Joe Ramante, where he in discussing about the heating of the dark matter. So you can have either like dark matter, dark matter scattering with the nucleon and transfer the kinetic energy to it. So they hit the object, or they can just capture and then they annihilate inside and also like hitting the object. That's for the fermionic dark matter, right? So depend on the model. So recently we also thinking about bosonic dark matter. That have different kind of hitting, but I will say I will send you that article. That's very nice article by Joe.
Nice. Yeah. Thanks.
Thank you for the talk. So regarding the detection technique using celestial objects, so as far as I understood, you are not doing any model-dependent assumption for regarding the constraint that you are putting. So you put some constraint on the cross section. So my question is there any model that is more constrained than others using this kind of observations or not?
So Okay, to be okay, so to have a statement that we do model independent is very strong. We actually have some model dependent implement in our assumption. So we must have like a dark matter interact with a nucleon or electron only, and then they can annihilate to produce some kind of a long-lived mediator or neutrino or etc. So that's already assumes a model. But if you go to for a specific model like WIM, neutralino, axion, etc., it will be very, very hard. So far, I didn't read, like I didn't know any article consider that direction. Because like if you go to a model, then you will have some suppression coming from the signal, right? You not only produce like photon or neutrino, you can also produce like a lot of particle coming from the annihilation, and that will suppress your signal. Yeah. So there's so in for my short answer, no. Okay.
Any more questions? If not, let's thank Tom again for his talk.
Thanks.